Okay, this is from section 3.8, problem 93, one of the homework questions we didn't have time for in class. So this is the function we're given, and we are supposed to find dy dx. And I think the instructions tell you to use logarithmic differentiation, but the other thing you should recognize is why you need to do that. So when you have a variable to a variable power, that's when you want to use logarithmic differentiation to help find that derivative. And the idea is that you're going to use the property of ln of a to the b is the same thing as b times ln of a. That's a property of logarithms from algebra that you're going to exploit here. Okay, so when you use logarithmic differentiation, two main steps. First is take the logarithm of both sides. And the idea there is then you use that property of logarithms to help rewrite so that the side that has variable to a variable power no longer has that power. And then you're going to use implicit differentiation to find the derivative. So for implicit differentiation, kind of two main steps for that. You're going to apply the d dx differential operator to both sides. So take the derivative with respect to x at both sides of the equation. And then you're going to use algebra to solve for dy dx. Okay, so let's go ahead and do that here. So if I start by taking the logarithm of both sides of the equation. So I have on the left side ln of y, and on the right side ln of all that stuff there. Then I use property of logarithms on the right side. So I have ln y equals, and I'm just using this property of logarithms that I have over here. Ln of a to the b is the same thing as b times ln a. And I rewrite that as x times ln of sine of x. And so now I no longer have variable to variable power. And so now I can differentiate both sides with respect to x. So I'm going to apply d dx to both sides. So again, we talked about this in class. Remember that that is d dx of each side. So you want to make sure you put that d dx out front and not at the back end there. So okay, so d dx of ln y equals d dx of x times ln sine x. And then you just differentiate both sides. On the left side, this is where your implicit differentiation and chain rule are going to come in. Derivative of ln of a variable is 1 over that variable. And then here where I'm differentiating something with respect to y, that's where I have that extra times dy dx. That's the implicit differentiation part over there. On the right side, notice I don't have any y's on the right side. The right side is just going to be an ordinary derivative. I do have some product rule and some chain rule on that right side. So product rule, I've got x times ln of sine of x, and then for the ln of sine of x I'm going to have some chain rule. So because the right side is a little bit complicated here, I'm going to go ahead and set up kind of a structure here for my product rule and my chain rule. So here I'll have the derivative of the first function, so that'll just be easy derivative of x, and then times the second function, and then plus the first function, and then here is where I'm going to need chain rule. The derivative of the second function, and this part will involve chain rule here because I'll take the derivative of the ln of sine of x here. Okay, so here we go. Let's go ahead and fill in derivative of the first. So that's just my derivative of x. That's 1. And then times the second function. So that's just the second function. I'm not differentiating it at all. Plus the first function. So that's just x. And then times the derivative of the second function. So I'll need chain rule here. So derivative of ln of a variable is 1 over that variable. And then I need to take that times the derivative of what's inside there. So times the derivative of sine x. Derivative of sine x is cosine x. All right, so there's what we've got. I'm going to write another line here where we clean that up a little bit. So I've got 1 over y dy dx on the left side equals, on the right side I don't really need that 1 there, so I have ln of sine of x plus, and then after the plus I have x times cosine x over sine of x. I could write the cosine over sine, or maybe I'll just rewrite that as cotangent. Either way is okay. It's just maybe a little cleaner to write cosine of x over sine of x as cotangent of x. All right, and then I've got one more step, maybe two more steps, depending on if you separate them out. I need to solve for dy dx, so I'm going to multiply through by y to do that. And when I do that, the other thing that you maybe will want to do at the same time, or you can do it in two separate steps, is you want to go back. The original equation had y equals sine of x to the x. So go ahead and back substitute in for y. Not every implicit differentiation problem has that, but if you start out with the equation solved for y, then you should be able to, at the end, get your answer dy dx all in terms of x, so you don't have any y's over there. And that would be especially important if you're going to do anything else with your derivative. All right, so ln of sine of x plus x times cotangent of x, and then all of that is going to be times the y, but the y was sine of x to the x. So I multiplied, at that step, I multiplied through by y to get the y, 1 over y off the left side, but then that means on the right side I end up with that whole thing times y over there. So that's what my sine of x over x is the y that I multiplied through by. All right, and I would probably just leave my answer in that form. The book might have done something else with that, or they might have the sine of x to the x written in front. So other than that, though, it's really just doing some algebra to tidy that up.